give someone a graduated cylinder and ask them to measure some liquid, and they come back with some value that's like 800.39753, get suspicious because you cannot get that many significant figures out of a measuring device like this. And similarly, if they were to calculate that, if someone were to calculate values and give you a value that's like 800.937393, get suspicious. In both of these cases, when we have more digits that, like, we put more numbers, it makes it sound like kind of like smarter, right? And you're giving a false sense of confidence about how good a measurement is. And so we use this concept called significant figures, where we only should report the numbers that will actually give this a sense, the true sense of how confident we are about the data. So if you're using a measuring device like this, basically you're only really confident about where it is between the two lines, and then you get like one guess. So you get those ones that you're sure about, and then you get one estimate. And so depending on how fine the gradations are, you can get more significant figures, you can get more precise. And then in both of these cases, though, the precision of that data is then going to influence how many sig figs you report when you do calculations, because 1 divided by 3, you might get like 0.333333, but that really doesn't have, you're not really more sure about that than you were if you were to divide 1 divided by 2 and get 0.5. So today, significant figures, how we determine them, how we measure them, how we report them, and all that good stuff. Significant figures, or sig figs, are digits of information that we know, or at least that we're pretty confident in. And when we report a value, whether this is a measured value or a calculated value, we're going to need to use a number of significant figures that conveys how sure we are about the measurement. In the case of a measured value, this is going to depend on our measuring tool. So say how fine the divisions are on your ruler. Whereas in the case of a calculated value, that number is going to be dictated, the number of sig figs you get is going to be dictated by your by your input, which is, say, a measured value. So it's really important to know how to determine the number of significant figures, as well as how to determine how to report the number of significant figures, both in those original measured values, the numbers that you calculate from those measured values, which then are limited by the significant figures of your measured values, as well as when you're reporting error. When you're reporting error for these values, you want to make sure that you're not kind of putting more digits than your error, So you're basically going to round to your error, and we'll get much more into all of this. But let's start with kind of just the idea of a significant figure. And to understand why it's important, you just have to think about dividing a 1 by a 2, get 0.5. Divide by 1 by a 3, you get 0.333333. If we report 0.333333, we're reporting more digits, but are we really telling you more information? Are we really more sure about the number than we were in the 0.5? No. Instead, we're kind of giving a false idea of precision, a false idea about how confident we are in the value. And so instead, we would need to round that number. And it would depend too if we're starting with exact numbers. So basically, an exact number is going to be a number that's defined, like a yard is 3 feet, or something that's counted, like there are 6 people. So no matter what a TV title might tell you, you can't really have 2.5 men. And instead, we would have a counted value, you would have 3 men. And so basically, in those cases, you have an unlimited number of sig figs, and they're not going to dictate how many sig figs your final number has or whatever. But we need to make it so that when we divide 1 by 3, we give the same number of sig figs as if we divide 1 by 2, at least when we report our value, assuming those were measured values, say. And so how do we actually determine, though, how many sig figs a number has? So to start, let's just basically, if there's a digit that's not a 0, that number is going to be significant. And so if you see a non-zero number, that number should be significant. Now, I say should because sometimes if you have the case where if you were to report 0.33333, someone might be reporting numbers and make it seem like they're significant, but those numbers actually wouldn't be significant. And so you need to make sure that you're not one of those people that's reporting a bunch of digits that if you were to just go by the rules of sig figs, you would say those digits were significant, but in reality, they don't really hold significant information. They were just kind of like falsely reported. They're giving you a false sense of confidence in the value. And so how do we determine how many sig figs a number has, and how can we report them correctly? So basically, if a number is not zero, this is going to be significant. The confusion comes when you have zeros. And when you have zeros, where the zeros are and where they are in relation to decimal points matters. So for a little intuitive example, imagine you have a theater row and someone comes in and they take a seat. And basically we're gonna have this theater row be filled from the left. And then later we're gonna have a detective come in and look and see where people are sitting and try to deduce some information. And so if that where that first person sits, that's going to matter. And so that's going to be a significant figure. So you're going to have that, you're always going to have at least one significant figure. And now the next person comes, and they may or may not leave seats in between themselves and that first person. And so remember, your seats are like your zeros. Your empty seats are like your zeros. And so maybe the first person smells bad, so they leave more seats. Maybe they smell good, or they don't smell at all, so they leave fewer seats. Basically, the number of seats between those people is going to matter. And so if you have a second number and there's zeros in between those numbers, then those zeros are going to be significant and they'll count towards our value. So in 101, we'd have 3 sig figs. In 1001, we'd have 4 sig figs. If there's zeros we're filling from the right. So if there's zeros to the left, if there's more empty seats to the left of that first person, that doesn't really matter. Basically where they took that choice to sit, that was the choice, and no matter how many left that wish they're left, that doesn't matter. So if you have zeros before the first digit, that doesn't matter. And this comes into play more when you have decimal points. And so basically those zeros to the left are kind of just setting the position of the first number. You can think of them as kind of just filler. But if the zeros are after that digit, if the decimal is preceding, then that zero does have meaning. So basically, if there's a decimal point before zeros, then those zeros do have meaning. And this can actually be a way in which we can make it so that we're showing more significant figures if we have numbers that end in zeros. So if we have, say, a 1, it's not the 1's fault that it ends in, if we have a 1.0, if we like measure that 1.0, and so we actually that is the true number of sig figs, or 1.00. If we really could measure out to 1.00, so we are sure about these values, it's not its fault that it was right on the line. It's not its fault that it was 0.00 instead of 0.01. If it was 0.01, we would be like, oh yeah, so that 1.01, that's 3 sig figs because we have a 0 in between our numbers. But if we have 0.00, well, now the zeros are after, but there's a decimal point. And so this is allowing us to see, yes, we are sure about these values. It's not the 1.00's fault that it would lie on the line, and these values really are significant. And so by using a decimal point, we can convey the significance of these figures. Similarly, if there's a decimal at the rear, then that 0 you hold dear. So if there's a decimal after zeros, then those numbers before the zeros are also going to be significant. So if we had 100 point, we had a decimal point at the end of 100, this would tell us that we had 3 sig figs here. When things can get confusing is when things get really confusing is when you have a number that ends in zeros and there aren't any decimal places. And so imagine you had 99 versus 100. Well, 99, that has 2 significant figures. And 100, well, if you just write it as is, that just has 1 significant figure. So just because you are have 1 more or something, that shouldn't make you lose significant figures. Or if you were to round from 99 to 100, you shouldn't be losing 2 significant figures when you do so. And so, but you should also not be gaining significant figures. So if you had a decimal point at the end, you would have 3 sig figs. So going from 99 to 100, we should be keeping the same number of sig figs. We shouldn't be changing our sig figs. So imagine if we had the same measuring tool, we would still have we should still have 2 sig figs, right? And so in order to actually convey the number of sig figs, we need to therefore introduce a decimal point. And we can't just introduce a decimal point at the end, because then that we'd be saying we have 3 sig figs. And so how do we keep saying that we have 2 sig figs when we're writing 100? And the answer is scientific notation. So in scientific notation, basically what we could do is we could write 1.0 times 10 to the second. And here the number of sig figs is going to be in the number of sig figs that is in the number that's multiplied by 10 to the something. So in this case, we could write 1.0 times 10 to the second. And this would tell us that when we're writing 100 this way, we have 2 sig figs in our answer. If we were to write 1.00 times 10 to the second, that would be 3 sig figs, which again, we could have written 100 and the decimal place at the end, but this is kind of awkward because people like sticking zeros after decimal places, but if you stick a 0 there, then the 0 is significant, so then it would say you had 4 sig figs. So yeah, so this is kind of awkward. Not that this isn't awkward, but this would tell you had 3 sig figs. And if you really wanted to write 100 where you really only had 1 sig fig, you would write 1 times 10 to the second. And this avoids the confusion and ambiguity when you have these values that end in zeros. So in the case of these ending in zeros, this is basically like if we go back to our theater example, and we have empty seats to the right of the last person that sat down. When the detective person comes in and they see all these empty seats, are those empty seats empty because no one wanted to sit there because the people smelled, or are those seats empty because they're cordoned off or something like this? And so no one could sit there. And if no one could sit there, well, then those don't really tell us anything that no one isn't sitting there. But if people could sit there and no one was sitting there, then that would tell us something. And so we can use decimal places to kind of indicate, yes, these seats were available or these seats weren't available. And so if you see a decimal place, this is going to tell you that the zeros that you see are going to be significant. Whereas if there's not a decimal place, then those zeros after the numbers aren't going to be significant if there aren't any decimal places around, any decimals around. And so scientific notation can help avoid the ambiguity. Okay, so this is basically how we can determine significant figures, and we'll get into some more examples later. But let's talk more about how we actually, now that we know how to report or like how to numerically what significant figures are, how to recognize them, and how to make our values so that they have a number of sig figs that we want. Well, where are these values actually coming from? And so these can be coming from measured values or calculated values, and there's going to be different rules for each of these. Now, when you have a measured value, basically the number of sig figs you have is going to be dictated by your measuring tool. And so if you have something with finer lines, this is going to give you more significant figures than if you had something with looser lines, because basically what's going to happen is you're going to read between the lines and then estimate between them. And so the finer together those lines are, the closer then the more significant figures you're able to get, the farther out your numbers are going to be, the more significant values you are going to have. And this relates to the idea of precision. And so yesterday we talked about the difference between precision and accuracy. So precision was how close measurements are to each other, and accuracy are how close measurements are to the real value. Now, if you have a number, you repeat a bunch of measurements, then how close those measurements are to one another would be an idea about precision. But even if you only take a single measurement, you're still able to give a value of precision, a value of how confident you are in the value, by giving the number of significant figures. And the closer together those lines are on the ruler, the closer the divisions that your scale or your balance can give you, the higher the degree of precision. And to kind of understand how this relates to our idea about the spread in the data or the difference between the different measurements, we have to think about how significant figures are determined when we're making measurements. How it works is that we kind of we can know the values that when there are line divisions. And so say if we had this, we would be able to say with confidence that this is somewhere between 2.5 and 2.6. But then we have to make a guess. So the 2 and the 5, those would definitely be significant figures because they're numbers that we're sure about. But then we get one that's an estimate. And so we get one estimate that is still a significant figure. But different people might estimate it differently. And so someone might say it's 2.52, and someone might say it's 2.53, and someone might say it's 2.56. So these people are going to have different values. But these values are going to be in the third decimal place. And so basically now you're still getting out to the 2 and the 5 with the so you get those two significant figures, and then you get the one that's the estimate. And so here you're still getting three significant figures. But if you start with a tool like a meter stick, well, here you're having to estimate between the 2 centimeter and the 3 centimeter lines. And so here you're only sure about this one place, and then you have the one estimate. So you only get two significant figures. And you can see how this relates back to the idea of precision, because you're going to have more spread in the data, more variability when there are bigger divisions, because it's going to be harder to estimate between them, and people are going to have bigger differences in their estimations. And so sometimes it can be kind of confusing when we're talking about precision in terms of repeated measurements versus precision in terms of a single measurement. But in the case of a single measurement, we're still able to kind of give an idea of precision, and that's going to be given by how many sig figs we have. And so the more sig figs we have, the more precise our measurements can be, is taken to be. But that doesn't mean that it's accurate. And so accuracy is how close the measurements are to the real value, and it's still possible you could have really precise values, but they could be inaccurate. So say if you were to measure using this more precise balance, but you forgot to take into account the weight of the weigh boat, you forgot to zero or tare it, well, now your value isn't going to be very accurate, even though it is precise. So when you're measuring, the number of significant figures is going to be dictated by your measuring device. If you're doing something manually, you're going to get the number of, you're going to get the numbers that you're sure about, the numbers between the lines, and then one estimate. And so you would say, get three significant figures in this case, or you would get two significant figures in this case. And now what if you wanted to go and use those values? When we perform calculations on values, we can often introduce like a lot of extraneous numbers, such as because you're measuring by things that don't divide evenly into one another. And so it's really important that you don't then report all those numbers, because then you'd be giving a false idea about precision. So just because you calculated a value, that certainly shouldn't mean that it has more precision than the value that you measured. And in fact, your calculated values are limited by the values of the significant figures of the values going in, by the precision of the values that go in. So the value that comes out of your calculation should not be more, you shouldn't be more confident in it than you were for the data that went in. So, but what's the phrase, like garbage in, garbage out? So if you have very imprecise data going in, your data coming out is going to be very imprecise, and it's at least going to be as imprecise as the data that went in. And so we need to make sure that when we're making calculations, we take this into account. And the rules for how we determine the number of significant figures for calculated values is going to depend on whether we're doing addition or subtraction, or multiplication and division. So when you add or subtract the decimal points to your facts, so your answer should have the same number of decimal places as the starting value with the fewest number of decimal places. So basically, the first decimal place, the first thing after the decimal, like the last numbers after the decimal place, remember those are going to be so these would be two significant figures, and this would be like five significant figures. But in the case of addition and subtraction, all we care about is the digits after the decimal place. So we go for the one that has the least number of digits after the decimal place. So although our answer is going to end up with three significant figures, this is going to have the same number, which is more than you went in the lowest number going in. It's still just at the same number of decimal places, the same number of digits after the decimal place. That's what's going to matter in the case of addition and subtraction. So in this case, you would round off your answer at one decimal place, and this would give you 27.2. Now, in the case of when you multiply or divide, then you need to consider both sides. So basically, the answer should have the same number of sig figs as the starting value with the fewest sig figs. So in this case, we are caring about the total number of sig figs, about our numbers going in. And in this case, we're going to round our value to the number of significant figures of the lowest value the number with the lowest significant figures. So here it's the number of significant figures that counts, and here it was the number of decimal places. And so there's different rules for when you're doing different calculations. So here are a couple of quick examples if you want to pause and pause the recording and try to solve them yourself, or just follow along. I'll give you a few seconds if you want to pause. Your time in order to pause is stopping now. Okay, so basically, starting with just determining the number of significant figures for 0.00908. So remember that leading zeros don't count. Those are kind of filler space. But now these, the non-zero numbers do count. And so the 9 and the 8, these definitely count. And sandwich zeros count too. So in this case, we would have 3 significant figures. Now, numbers at the zeros at the end also count if there's a decimal. So in these cases, we would have 5 significant figures. So we have 3 numbers that are non-zero, so those count. This zero sandwich, so it counts, and this zero is at the after a decimal point, so it counts. In this case, we have 4.20 times 10 to the third. This is an example of how we can use scientific notation in order to kind of dictate how many significant figures we have. So in this case, we have 4.20 times 10 to the third, which if we want 1, 2, 3, that would be 4,200. And if we were to just report 4,200, it would look like we would have 2 significant figures. If we were to report 4,200 and then a decimal at the end, then it would be 4 significant figures. But we only have 3 significant figures, and we only want to report 3 significant figures. So we can report 4.20 times 10 to the third. And if there is no decimal, then the zeros aren't going to have meaning. So this is what we looked at before, where if we were to just write this without the scientific notation, 4,200, we would only have 2 sig figs. So that was an example of counting sig figs. Now let's talk about calculations. And so if we have addition or subtraction, now here we're going to look at the number of decimal places. In 2.5, we have 1 decimal place, and in 3.01, we have 2 decimal places. And so when we round, we're going to have to round to 1 decimal place. And so we round to 5.5. Like I mentioned, if you have 0.5 or more, you round up. And if you have less than 0.5, you round down. Okay, so what about when you have subtraction? The rules are the same. So with 8, we have 0 decimal places. With 0.7, we have 1 decimal place. And so our answer is 7.3. We're going to need to round it to 0 decimal places, so 27. Multiplication and division, here the decimal places don't matter except in terms of determining how many significant figures there were going in. And instead we care about how many significant figures there were going in. And so in the case of this, we have 12, which has 2 significant figures. We have 4.0, which has 2 significant figures, because remember, a 0 after a decimal point is significant. Our answer is 48, and we report it as 48 with 2 significant figures. 12 divided by 4.0, this is going to be 3.0 because we have 2 significant figures in both of our incoming, so we need 2 significant figures in our outgoing. And so we would report this as 3.0, not as 3. This last one's a little more tricky. So we have 12 times 4, and so basically we have 2 significant figures and 1 significant figure. And this is assuming that these are measure values and not like exact values, so they're not counted. These are measured values and not counted values, so they're not like people where you would have an unlimited number of sig figs. Instead, we're saying that these are going to be, we're actually reporting sig figs here. So we have 2 sig figs and 1 sig fig. And if we multiply these, we get 48. And so we're going to need to round. And so we would round up, we would round to 50. But if we write 50, well, here technically this is only going to have a single sig fig. And this is going to be correct. However, this is kind of ambiguous because basically when people see a number like this, it's not very clear that there's only 1 sig fig, and it's kind of hard to tell whether people just wrote 50 or they're writing 50 and they really they're really caring about the sig figs. So a lot of times people are kind of careless with their sig fig reporting, but if you really want to show, yes, we only have that 1 significant figure, you can show this using scientific notation by writing 5 times 10 to the second. And so here you're showing, yes, you have 1 significant figure here, not 2. And if you had a number where you wanted to say 50 was actually 2 significant figures, you could put a decimal point at the end. So in all these cases, the decimal point is helping us with our significant figures. Rounding is helping us, and we're having to determine where to round. Another place with rounding that can get people into trouble is when you're rounding your error. So your error can be something like your standard deviation or standard error. It can kind of tell you about how representative a value is or how close together your values are. And so basically you often have the error reported as plus or minus something, and it's kind of going to be like your kind of wiggle room in your measurements. And basically, when you report this error, you're only going to get one significant figure for the error, and then you're going to have to round your measured value or your calculated value in order to match the number of significant figures, in order to match the decimal place of that error. And so say you calculated an error of plus or minus 7.3. Well, if you're not sure about that 7, then you're definitely not sure about the 3. And so when you're reporting this error, you would round it to plus or minus 7. If you had a 0.073, then it would be plus or minus 0.07, et cetera, et cetera. And so remember, the leading zeros are just fluff. And now you're going to round your data to match the decimal point of the error. So if you measured or calculated 2.53 for your data value, but your calculated error was plus or minus 7, you would report this as 3 plus or minus 7 because you need to round your data to match the one significant figure error. 2.53, if your error was 0.7, well, now you would do 2.5 plus or minus 0.7. And only in the case where you had your error out at the 0.07, were you able to report your full 3 sig figs that you put in, the 2.53 plus or minus 0.07. Now think about why. So basically, if you were to add 7, you would overlap all of these other digits back here. And so it wouldn't be accurate, because if you're not sure about this first digit, you're really not sure about these digits out here. And so you're giving a false idea about precision when you're using all of these digits if your error is going to be larger than those digits. And so hopefully that helped you understand the, I have a whole post on reporting error, but basically one significant figure for your error and then round your numbers to match it. And check out that post if you want more details about it. So in summary, the number of significant figures is going to depend on how you're measuring, like what tool you're using to measure. And the finer the gradations of your tool, the higher the precision of the tool, the more significant figures you can get out to. When you then make calculations from those numbers, your calculations are going to have to be modified. You're going to have to round your calculations in order to fit the number of significant figures of your input data. And your output data can't be more precise than the data that went in. So how do we actually report the number of significant figures? Well, if any number you report is not a 0, that number you're saying is significant. If there's zeros in between non-zeros, those zeros are significant and they count. If there's zeros in the lead, then erasing can proceed. And so basically zeros before a number are just serving as placeholders and they don't count as significant. If there's a decimal, basically the decimal is going to help show that numbers are significant. And so this is a tool we can use if we have numbers that say end in zeros and it wasn't their fault, they just happened to fall in the line of the measuring tool or something. So if there's a decimal before a 0, the zeros that come after it are going to be significant. And if there's a decimal after a 0, the zeros before the decimal are going to be significant. If there's no decimal, then technically there wouldn't, only the non-zeros would be significant, and the zeros would just be placeholders. But often you have a value like 99 that you might round to 100, and you might forget, oh, well, this is like, now we have to take into account that I just went from 2 significant figures in 99 to, if I write 100, it looks like I only have 1 significant figure, but I really still have 2 significant figures. Now, if I were to write 100 decimal place, then that would have 3 significant figures. If I wanted to actually convey 2 significant figures, what I could do was I would be able to write 1.0 times 10 to the second. And so using scientific notation can help you avoid that ambiguity. And I should also note that people are often pretty lax about significant figures, but it's really important to keep in mind, especially when you're reporting your error. And so hope that helped.